Hello, my name's Court Dugan. I'm from FSM Labs. What I'd like to do is take the next 20 minutes or to 25 minutes and talk about TimeKeeper. It's our suite of products for time synchronization, time serving, managing, auditing, and the like. It's a complete ecosystem, top to bottom, software and hardware. It's a complete solution in and of itself, but it does work with your existing appliances, your existing software, and the like. So it's not all or nothing. And just as a note here, I'm not going to PowerPoint you to death. I have 2 slides, and I'm going to jump right into the demo of the software and the hardware and show you what we're going to be doing. Now, on the bottom left, you see my name. You also see the last time this video was updated. This technology evolves very fast, and we're often driving. So what we'll do is we'll be updating this video to reflect the state of the art and what's currently the case, and we'll be updating that date as well. So what I'm going to be showing you here is going to be our hardware and our software. Now, this software that we have, TimeKeeper, is able to run on any platform. You can put it on your own hardware and build your own time-serving appliances with a GPS card and our software and some simple configuration, or you can use our ready-to-go appliance with some of its features. I'm going to be using our hardware just because I'd like to show off some of the features and what its capabilities are. So let's move on. So here's the last slide. What I'd like to do before we go on to the demo is show you exactly the hardware we'll be using, just so you have some context for what we're going to be doing. The device is called the TimeKeeper Enterprise Grandmaster. That's from us, FSM Labs. It's also branded under the name VelaSync from the company Spectracom, one of our partners. It's available from both. Now, top image, you see the front. It's a 1U rack mount system. That's pretty traditional for these devices. You plug it in, you rack it up. It's a 1U device. You give it power, you give it network, you give it a GPS connection. It gets time and it serves time. Now, traditionally, these devices were 100 megabit, single power supply. They had very few features. They did not have the latest protocols. They didn't have the latest networking technology and the like. So they really didn't fit in with the enterprise data center very well. Ours does. Down at the bottom, I'll just hit really quickly some of the unique features of our system, not retread some of the standard features. So we've got the GPS antennas and the timing signals in the top right of the back there. It's pretty standard. Below that, you'll see 2 SFP Plus connections. Those are our 10 gig interfaces. We have optionally, we have standard 2 10 gig, optionally 2 additional 10 gig interfaces. The reason that's important is, number one, typically these devices have 100 megabit connections, which is quite old and certainly doesn't fit with modern technology. 2, the speed is not so important. The latency is not critical. The key is when you connect 100 megabit or 1 gig into a modern switch, say an Arista or a Cisco, it is designed to do 10 gig, it's cut through one direction, store and forward the other direction, and that causes serialization delay. The end result is packets traversing that link are asymmetric. That is, it takes longer one direction than the other. That confuses time on the client end, so they will see a bias of about 4 to 5 microseconds. So right out of the box, you have an error of 4 to 5 microseconds. Not even counting in network error, client error, server error, and the like. So this fixes that and allows you to manage devices like they should be managed in a modern data center. Towards the center of the box, you see our 5 1 gig interfaces. Again, not 100 megabit, we have 5 1 gig. So those are standard as well. Moving over, you see we have a VGA and a USB and a PS2 console. You can connect up pretty much anything to this device, get onto it, configure it, query it, and the like. We also have RS-232 for configuring through various muxes, various remote devices, even just a PC connected up to the thing. This is helpful for folks in the data center, possibly remote hands, to get at the box, configure it, rack it up, and go. You don't have to find a web browser to connect up to our system, although we certainly prefer you use that because it's much more powerful and useful. In a pinch, you can do this quite easily. We also have a system management port. That's IPMI, so you can get a virtual console to the device from wherever you need. You can check the health of the box, you can monitor the chassis status, you can reset it, and the like. To the far left, you see we have 2 hot swappable redundant power supplies. The MTBF on power supplies is quite low. In almost any modern system, they're the highest rate of failure devices that you have, so we have 2 to keep the box up, serving time, no matter the situation. You can pull one out, put a new one in. They're commodity devices, they're fairly inexpensive, they're easy to replace, they're easy to supply you. And we have alerting and monitoring built into the device to let you know when something fails. Not shown here, we have two rotating disks on the device, each with a storage capacity of 250 gig. The reason we have so much storage is that we log everything, every timestamp, every update, every event, not only on this device, but devices feeding this device. In addition, every device that this is feeding in turn, we log. That way you get entire enterprise visibility and logging on this device. Now that's accessible through our GUI. You can go back a year, 2 years, a month, a week, a day. Whatever you need to do and whatever you've configured, the data is available. We also have that data for all of your systems. Now, you can leave it here. It's an open format. It's human readable. It's text. We document it thoroughly. We have a number of tools for processing it, but you can easily pull that data off and store it and process it yourselves. We have a number of ways of getting at the data. You can download it through the web GUI. You can SSH into the device and download it. You can stick a USB stick in and copy it off. Whatever works for you. Most of our customers like to automate that process, so either they leave it on our box and process it there, or they will nightly copy it off and archive it with the rest of their logs. This is useful because you may be in a situation where something occurs on your network. 2 days later, you want to go see what happened. I need some data. I want to find out what happened to timestamps, who thought the wrong time, and the like. You can see that all snapshotted for you. Additionally, if you have auditors come in that want to see your timestamps, they want to monitor FINRA OATS compliance. Are you guys monitoring your time? Are you actually keeping on point? We have that data. We can show them quite clearly and quite conclusively that that's the case. Now, I mentioned we had two disks in way of getting to redundancy. Those are mirrored so that one fails, pull it out, put a new one in, and you're up and running. So just like the power supplies, we have redundancy built in with the storage as well. All right, let's go on to the demo. So what I have here is the status page for our Grandmaster appliance. I've logged in to save a little bit of time here. What we've got set up is one of our units in a deployed configuration, just like you might find in any data center. And you would replicate this across your enterprise and however many data centers you have. Now, what we're doing is we're serving multiple clients from TimeKeeper software clients. There's some hardware devices on the network here that I'll be showing you. And also we have some other vendors' devices and software as well. And we'll be talking through some of the configurations. So on the status page, it's pretty much what the name implies. It shows you the status of the device. Up at the top, we see it's currently actively tracking. It's tracking a primary GPS source. Everything's looking good across the hardware health status. The power supply, both systems are good. It will alert and send out SNMP, our syslog messages. It'll send out emails. Whatever kind of alerting you need if there were a problem there. Inlet temperature is good. It's within range. That's 84 degrees. We keep our data center pretty hot in order to thermally stress the devices, since a lot of devices out there are extremely sensitive to temperature changes, even half a degree Fahrenheit or so. And we want to test across the entire range. We also show that the RAID status is good. Both disks up and healthy. One were to fail, just like any of the other parameters, we'll send out alerts, we'll let you know, and it'll tell you which of the devices has failed. Same with the power supply. So here we're currently, our primary time source is the GPS and the oscillator. We can have as many backup time sources and cross checks and spoof detection sources available, but the primary here is the GPS. We show that the status is good, how many satellites we can see, maximum signal strength, the internal temperature of the GPS, which we note if it's out of range and tolerance. Below that, we see the current source accuracy is 82 nanoseconds. This is just a quick snapshot of the whole system. Nothing really detailed here. We'll see a lot of detail later on. How long the box has been up, the software version that's running, self-test is passed, and the like. So let's go on to the next tab. So here we're going to jump a few tabs to the right so we can see something that's a little more interesting, a little more useful in day-to-day operation. We'll cover the others in just a minute. So here we're looking at the time quality tab with the live graph subtab. What this is going to give us is exactly that. It's a live graph of the time and quality that the device is receiving. So here on the bottom left, you see that we're using the internal GPS. That's what the device is. And we're reading time from it. Whether the GPS is connected or not, we'll be able to get stabilized time off that oscillator, even in a GPS-denied environment. Then over here to the right, you see the y-axis is the amount of time. Here I have it set at 10 minutes. We can also move that around with the sliders. The x-axis, the x-axis. The y-axis is delineated in seconds. So here we have 0.000 and on. And what we can do is we can zoom in on that, and we can see that we're roughly in the range of about plus or minus 200 nanoseconds accuracy. But we have quite a bit of noise in that. This dotted green line, you see, is the raw sample from the GPS device. That is, every sample that we read, we graph it so you can see what the device is generating. The solid green line, that's much cleaner down at the bottom, that's in fact our smooth filtered time. That is, TimeKeeper building a number of clock models, discovering some of the sources of noise, and removing the signal, extracting the signal from that, and just discarding the noise. That's one of the powerful features of TimeKeeper. We're able to enhance extremely accurate devices with extremely accurate software and get almost orders of magnitude improvement on that. Now, because of the clutter, you'll notice I zoom into 1 minute, yet we still have these periodic spikes. The raw noise is still quite great, but it looks like the real signal is extremely accurate. To clear up our graph a little bit, we click on raw offset to remove that so we can just see the estimated time offset. And we see 5 nanoseconds, -5 nanoseconds, and the like here. We'll look back at 10 minutes. So we're roughly in the plus or minus 100 nanosecond range, which is about what we'd expect here. This is in a pretty noisy environment. That is RF noisy. Our lab is designed that way intentionally to test our equipment, and the temperature is really not what you might expect from a typical data center. So in addition to this, we have the frequency graph that will allow us to look at the frequency of the device. That is, how has it been changing time? How has it been changing the rate of the clock over time? Oscillators on motherboards, oscillators and GPSs on desktop PCs and servers, they change frequently. That's not unexpected. It's the nature of the device. Additionally, when temperature fluctuates, even by a small amount, that is, the air conditioner in the room cycles every 7 minutes. The cold aisle becomes colder, the warm aisle becomes warmer. You'll see these kind of oscillations in the frequency of the device. After the device has been up for a while, if you take a look at it, we can see that the initial slew-in was a good deal. It's been slowing down just slightly. So we can see that we're discovering that, correcting it, and that's why we're keeping such accurate time, because we're able to measure that frequency change over a long period of time and cancel that out. Here we also have the one-way delay. That is the amount of time that is required to read from the device. This is not terribly useful for a GPS that's a local device built into the system, but it is quite useful for network devices. You can discover network problems, network asymmetries, and the like by using this. And we have some automated facilities for discovering that sort of thing that I can show you later. But since we're using the GPS right now, I won't cover that. We also have the snapshot view, which gives you a very simple snapshot in time, an instantaneous measure of the accuracy of all the time sources, all the devices, all the clients, which I'll cover in just a moment. But the live graph is a lot more useful. The snapshot view is very handy for those that want to use our software on their own systems that are very underpowered, 400 megahertz embedded devices and the like. Not everyone runs this software on one of our devices that is a large enterprise Grandmaster, but you can build your own Grandmasters quite easily and do that with the software. And we have facilities for underpowered or lower resource availability type systems. Now here I've switched to the Time and Quality Live Graph Clients tab. What this is showing me is the same information the Source tab is showing me, or pardon me, Sub tab is showing me, but for all the clients. It is everyone getting time from us and everyone getting time from someone else. So we can see with one pane of glass what's going on. How is the system behaving as a whole? With one pane of glass, we can see our entire enterprise and get real information without digging through log files and different web pages. That's critically important to us in every design decision we make for the software. So here, we're taking a look at the same sort of information. I'm not going to walk this through. It's a bit noisy here. We have it configured intentionally to be noisy to show you the graphing capabilities, but you can slide, you can select 1 hour and the like. Here I'm going to add a few of our additional clients. Notice this system is getting time from multiple sources. Some of them are quite noisy. They're moving around just to make sure we differentiate between them. And that's being graphed here. Note we're seeing that the raw noise is jumping around. The cleaned up noise is actually quite sensible. Now, what I'll do is I'll take those sources off. Now here what I've done is I've deselected those so they're out of the way and we don't have to see their information. And then I've selected one of another client's graphs. So here I'm showing Court WinXP. That's my name. That's my laptop named WinXP for antique reasons. It's actually a Windows 7 box running Domain Time 2 from Grayware. They produce a PTP and NTP client. That's out there driving time on that box, just to show you that we can interact on the management pane with those kind of systems as well. Get as much data as they provide. Most other systems that are not TimeKeeper based don't provide very much information for this sort of thing. We don't care. We go out and get every piece of information that we can and consolidate it. So we bring the whole estate together. And that's what we're showing here, is we're able to graph that pretty clearly. So here I've switched to our map tab. At this zoom level, it doesn't really help out a lot. But what's going on here is we're mapping our network, our time network. Every time packet we see, every bit of information we see, we map. So we can dynamically show you what your time network looks like. It's useful for two cases. Number one, you want to see, does your Visio network diagram of time look like what your actual network is? We can actually map what's really happening in physical reality and show you, is that really the case? Two, we can actually show you what the physical reality is when you're presented with a network you don't understand. Multiple vendors, multiple partners, third-party systems set up that are providing you time. You have no idea across multiple data centers. TimeKeeper is able to go out and find out what's going on in the outside network and tell you who's getting time from whom. So you can address and find single points of failure. Now, to further illustrate that point, I'm going to zoom in. First off, I've fixed positions. You can drag systems around and they will dynamically reallocate to make the map more clear. I've stopped that just to speed things up here. So, first off, we've got this system. We're showing some information, last updated 0 minutes ago, and at the top left of this map up here, I'll hover over it so you can see it. It shows you exactly what's going on. Now up here we can see some of the systems in our lab. Test 8. It's updated 220 minutes ago. We'll skip that for now. Here I've pointed the system at the Apple Time Network. That is all the time that Apple gets time from. Here we see that there's a hierarchy of systems, time.apple.com, various IP addresses used. Eventually, that bubbles up to tick.apple.com. We can see its accuracy is roughly 396 microseconds, not terribly good, and it's connected up to a GPS. We can see that from the blue line here. So eventually it bubbles up to a single point of failure with mediocre accuracy. That tells you something about how this time source is working. So normally one would assume this entire constellation of time servers would be quite accurate, but in fact it relies on one time server that's tolerably accurate. And this information is just gleaned from what we can find on the internet. We query a server, we query the next, and so on, and develop this entire network. Additionally, what we've done is we've queried the Dell network. Where does Dell get time from? Here we see that it gets time from, let's look at this, a CDMA server. CDMA is a cell phone network time server available from one vendor. They provide that. It's available only in the US, and it will get time from the cell phone network. And it was roughly, at best case, 10 microseconds accurate over the CDMA network. Here it's providing that time. And we can see it's switching between different servers periodically. A local CDMA server, and it's bouncing up over here to another CDMA server periodically. Now here we zoom in on the NIST servers. A little more reliable, the US government. This is official time, something that FINRA OATS compliance will often require. And what we can see is the servers we're querying here, time A, time B, time C, NIST.com. The graph updated here, so let's zoom back in. NIST A, NIST B, NIST C. And it eventually bubbles up via the blue line to an ACTS server. That's a modem-derived time, which calls back to Boulder, Colorado, gets the time, and updates to the official US time. That's what we're seeing here. So you can see that the NIST servers, one hop from this time server with, what are we looking at? They claim 0 offset. A little optimistic probably, but they're quite close to the ACTS server. They're probably reasonably accurate despite that modem connection, and that's what we see here. Over here, we see some other systems in our lab. Here we have test 3. That's one of our network time servers, and in the top left you can see we're pulling a lot of information away from that time server. The version of the client, the software version of the software information about the client, and so on. Now here we're looking at the WinXP server that I mentioned before, which is in fact my laptop, and it's showing that it's running Grayware software. Up at the top left you can see this, and the domain kind 2 client software, and the serial number and the version number and the like. We're able to pull information like this out of clients that are not our own. We can work with a multi-vendor environment. And that's what I'm demonstrating here. Now here what I'd like to show is the Amazon EC2 service. We have a number of devices out in Amazon's cloud, and we're showing that you can get disciplined clear time through the Amazon cloud, but you have to be very selective in which client software, for example TimeKeeper, or otherwise you use. Also, you must be deciduous in which servers used for receiving time. If you were to follow Amazon's recommendations for the EC2 cloud, you would use 0.amazon.pool.ntp.org, 1, 2, 3, and so on. They, in fact, resolve via DNS to the myriad of pool.ntp servers, which is just the wild internet that can be inaccurate beyond belief. Often they are off by a second, and in fact right now, as of recording this video, they are off by 1 second exactly because they've begun advertising a GPS, and some servers on the internet, the GPS signal has begun advertising a leap second, and some of the servers have interpreted that as a currently occurring leap second, and they have jumped forward by 1 second. And some of the systems are advertising that. So it's quite undisciplined, and without TimeKeeper's source check capability to reject false leap seconds, you're really left unguarded. Your system would be willing to jump by 1 second for no good reason whatsoever. TimeKeeper, however, is able to enable the source check feature that we have, and it's able to cross-check time. If any time server appears to be in error, false leap second, frequency is out of range, or time is out of range by any measure, it can switch away. So if you're on the EC2 cloud, you would, with a traditional client, be just jumping. Here, we're running TimeKeeper, and it's in fact carefully deciding that's not appropriate, that's the wrong thing to do, send out alerts via the standard mechanisms, and use standard time. So here what we see is, here we have the Amazon servers eventually bubble up to a single point of failure. That comes up to a number of other time servers that it's receiving time from, and they vary wildly across the internet. Over time, these shift and come and go, often across continents for no good reasons whatsoever, and then bubble up to an iRig time server, a legacy sort of technology, pulse per second, GPS, through various networks, and you can see that there. Only TimeKeeper gives you the ability to see this and to actually diagnose problems like this and see where your time is coming from. Now here I've switched to the far right tab, the support tab. One of the more mundane tasks, but a critically important one at the appropriate time. A lot of devices out there, a lot of software out there requires you to take screenshots, copy files, email, this and that. We've tried to automate that procedure both for our convenience and for yours as much as possible. So here you're able to, through the GUI, select automatically upload logs. They'll upload them to our server via FTP and then collect TimeKeeper logs. That will collect a file, it'll put it in temp, it'll tell you where it is, and it will try to upload it if you've selected the appropriate box. It'll also give you an option to download that so that you can put it on your own system. If you're firewalled or you have a lab setup that won't allow that, you can easily get it to us through some other mechanism. We have FTP, we have a web upload, you can email it to us, whatever works best. But we're trying to simplify the task of supporting you and being supported. When you have an issue, we don't want to go back and forth constantly with, please take a screenshot of that, please copy this data, take a look at that and tell me what it says. We want a snapshot to find out what happened, what's the problem, and get a good capture of your system. You're able to leave that box to automatically upload unchecked, download the file, look at it to make sure no information that your corporate policies don't permit go outside of your network. Remove that information and then give it to us sanitized so that it's appropriate. So here I've switched over to the configuration tab and the TimeKeeper configuration sub-tab. This is the sub-tab that deals specifically with time services, receiving time, serving time, time options, and so on. The other tabs deal with networking, system management, and that sort of thing. I'm not going to cover that right up front. I'd like to talk about the time serving and receiving first. So on the left you can see, and I'll scroll down here so you can see a little bit more, we have a ton of options. We can configure quite a few different capabilities, and it gives you a lot of power. Got some verbose options here as well. I'm not going to hit that right now just because we don't really have time in this video. What I would like to show you, over to the right, we have the Sources sub-tab. This will show you all of the time sources the device is getting time from. So here we have configured, I'll expand this tab, the primary time source, marked primary, source 0, in priority order, lowest to highest, highest to lowest, going from 0 to 49 potential sources. It's our internal GPS configured and the internal oscillator as well. Should that fail, we'll fall back to the next source, source 1, source 2, source 3, source 4, and so on. We also have some options called source check, I'll talk about them a little bit later, where we can cross-check them against one another. So that if one unit goes bad, one unit in one location and one data center is being spoofed, their GPS spoof attack is going on, there's an NTP problem, hardware has failed, software has failed, something's going on. It can detect that, alert you, let you know what it's going to do to fix the problem, and switch to other time sources. So here I'm going to close that tab up. Note, we can delete sources quite easily here. We can also grab a source, change the priority of the source, allow it to complete. And what we can see here is now as our backup source, what we have is we have PTP as well. In the lab, we have 2 of our grandmasters. Typical deployment in the data center is you have a primary and you have a backup. And those 2 will talk to one another to cross-check time. If one fails, the other one immediately picks it up. And also if one has an error in time, a false leap second, any kind of issue like that, the other can detect it. It can also detect it itself by cross-checking with the others. And this can work throughout data centers as well. So you can talk Chicago to London, London to New York, and so on, so that everyone knows what time is. I'm going to close this tab, scroll down a little bit, and what we've got configured here is one of our local NTP servers. It's one of the lower quality systems. It doesn't have a GPS. It doesn't have a really good feed. I have that just for showing you. We'll look at that in the map a little bit later. Here I also have the standard pool.ntp.org sources. We've got those to cross-check time and to demonstrate, just to show that we can. We have quite a few of those. Also, we have time.apple.com. We're sourcing time from there. And then the Amazon servers. Those actually end up resolving to the standard pool.ntp.org servers. It's the official way Amazon EC2 Cloud provides time. But when you query them, they end up being some random server on the internet rather than something that's really a curated, cleaned up time. So you need some reasonably intelligent software in order to detect time problems. It's Not at all a surprise that the internet itself often has false leap seconds being projected as we film this. One is being broadcast right now because of some GPS data that came in. Bad time servers on the internet started claiming a leap second had already occurred. These sort of things are very common with internet servers, and you need some smart software to cross-check that. Here we also have the NIST servers. Much better quality, official U.S. government time from NIST, available via PTP, and a few other servers I have set up here as well. And you're always able to add a new source. Now, I'll grab one of these, and I'll just note what we're doing here. Here, we have major and minor time. We're able to actually split time so that time of day can come from one low-quality source, but we can pull in the very precise intrasecond time, intersecond time via another source. So we're able to take a pulse per second or another signal and combine it with other sources. That's what we're seeing right there. Here, I'll go over to the PTP servers. What we're looking at here is the ability to add and create different PTP servers. So PTP version 1 and 2, which domain, the rate, priority, and so on. A lot of configuration options. Here what we're able to do is we're able to select from all the interfaces we have. We bind it to an interface. That is how PTP works. We provide that mechanism as well. All of our interfaces, you'll notice, are listed there. We have quite a few. We also have one additional one, ETH 2.5. I have that there because I've configured a VLAN to show you that we can support VLANs, as many as you like, on as many interfaces as you like. And you can select them for PTP servers as well. We also have some options here for doing hybrid mode and so on. Here I've switched over to the networking subtab. Typical networking settings. Not going to cover much of that at all. It's not terribly interesting. What I will tell you is, I mentioned IPMI earlier. Here we have the configuration for IPMI. You can control that here, enable it, disable it, change the network parameters. Also, we have ETH0. It's configured. It's not DHCP. It has a static IP. No default route gateway address for it. And one thing that's extremely useful, although it seems obvious, is the link status. Often these devices are installed by remote hands. You may never see the device, but you're in charge of configuring it. You tell the data center people, connect the first Ethernet port and the third up to this, and it must be this speed, and use this SFP adapter and use this switch. They've never seen the thing before. You've never seen the thing before, and often there's miscommunication. We can short circuit that really quickly right here. You can immediately see which link is connected and what speed. So here we have ETH0 connected up at 1 gigabit. And then here we have our 10 gig interfaces. And then here we have our VLAN interface. They're not connected, but I'm showing you that you can actually query them all. You can add a new VLAN quite easily as well. Root interface, the various tags, and the different kinds of information you want to put in there. Here we have system and service management. Again, standard stuff for an appliance. Start and stop the system. Enable root login, enable SSH login, add users, remove users, give read and write privileges, factory reset, shutdown, save the configuration, restore configuration when you're changing devices, that sort of thing. We also have syslog, SNMP configuration, so the device will alert and send out the appropriate messages, and then different authentication types, Radius and TACACS primarily. We also have HTTPS certificates that you can upload and generate. Here, software updates. Easy it can be to do a software update. Click on Update, downloads the software, compares it to the current version, asks for permission, upgrades, and reboots. You could also download directly onto your workstation or your laptop from our site. You can get the firmware and the software that you want to install and install it directly yourself so that you aren't beholden to our servers or connectivity to the general internet in order to do the upgrades. So that was a rather quick overview of some of the major features of the software and the hardware that is all under the TimeKeeper umbrella. If you have any more questions or would you like some detail on specific subjects, we're more than happy to talk to you. We have evaluation copies of our software available, and we have a demo pool for our hardware that's available as well. So please feel free to check out our website, send us an email, and if you have any questions, we'd love to hear from you. Thanks for taking the time.